Hello, everyone. Mr. Minnick is my name, and math is my game. Sorry about the sudden change in volume there. Mr. Minnick's my name, math is my game, and today what we're looking at is the unit circle. The unit circle. And the next part of this starts to get into the coordinates all the way around it. Gets into the coordinates all the way around it. In my Algebra 2 class, we're kind of diving into this unit circle, and I mentioned the first lesson that memorizing stuff is real critical. Being able to have a good memory and memorizing all the different components of it. So the last time, just to recap where we left off, we said over here is a 0-degree angle and 30 degrees, 45, 60, 90, 120, 135, 150, whoop, not 1500, 150, 180, 210, 225, 240, 270, 300, 315, 330, and back around at 0 is also 360. So that was where we left off yesterday. And we also talked about the coordinates if we go here to the North Pole and over here and down here and over here. We talked about those coordinates, and those all are based on the fact that the center of the unit circle is at the origin. So if we could imagine moving from the center out to the edge, if we realize that a radius is 1 and that distance is 1, of course, the coordinates over here are 1, 0, and over here are -1, 0, 0, 1, and 0, -1. So that's kind of where we've gone so far. What we're going to look at today has to do with a piece of clothing that I think is making a comeback. People don't dress up like they used to. Back in the 30s, if people just went out into town, they dressed up. They wore really nice clothes. Clothing back then probably cost a little bit more, or maybe people just made it. But anyway, there's a piece of clothing that men usually wear around their neck that not many people wear nowadays. And there's a kind of, women wear this in their hair sometimes. There's a type of pasta, bow tie. So what we're going to talk about today are bow tie angles. Bow tie angles. Bow tie angles are pretty cool. Real cool. So these bow tie angles, if you graph them on a unit circle, they actually look like bow ties. And what comes into play with these bow tie angles is the idea of symmetry. So what I'd like to do is just, we'll look at one particular set of bow tie angles. Probably the one that makes it look most like bow ties. So here at 30 degrees, over here at 150 degrees, down here at 210 degrees, and over yonder at 330 degrees. So it kind of takes a little bit of creativity to think about it this way. So I'm going to go ahead and go across here and across here. And if I fill all that in like so, maybe now I can get my paintbrush. I'm not very artistic, but I'll get my paintbrush going. And I never was any good at staying inside the lines, so please don't be mad. Maybe I should have some of our more artistic students do this for me. But there it is. There's the bow tie. What do you think? So the deal is all those angles have similar traits, similar properties, similar things about them. We're going to be talking about the coordinates, and we're going to get to that in a little bit, but we're going to be looking at the coordinates at those points. Okay? We're going to be looking at the coordinates of those points. And the interesting thing is all those points, all those angle measures, I should be saying, they all have the same numbers. The only difference in the numbers is the SIG and S, the signs. The only difference is the SIG and S, the signs. Remember how the signs go in the quadrants? That's going to come into play. Okay? So bow tie angles. Let's look at the next bow tie angle while we're at it. Just so everybody kind of, for the completion's sake, there's more bow tie angles than just those. Because if we go to the 45 degree angles. So this one's 135. This one down here is 225. This one down here is 315. So same kind of thing. I'll go ahead and connect all those up. So like that, and like that, and like that, and like that. So there's our bow tie, and that's a little bit taller of a bow tie than the last one. I think I might be able to stay inside the lines this time. A little better. There we go. So it looks like a bow tie too, doesn't it? And then lastly, 60-degree angles are also going to be bow tie angles. 60-degree angles are also going to be bow tie angles. So if I come up here to 60, and I go over here to 120, and I go down here to, what would that one down there be? 240, good. And then this one over here is going to be 300, I believe. Okay. So again, this is also a bow tie angle, and this is a really, really tall bow tie angle there. Okay. So the bow tie angles, all the bow tie angles. Okay. So today, according to the plan, we're going to be looking at special right triangles and all the coordinates. So I don't know who you had for geometry. Well, I know who some of you had. I know at least two people who are in this class normally had me for geometry. And in geometry, you study those special right triangles. I don't know how much of that you recall. But in geometry, special right triangles, special right triangles, not to be confused with any old right triangle, special right triangles are ones that are 45, 45, 90, and ones that are 30, 60, 90, and also ones that are 60, 30, 90. And you could argue that these are essentially the same. So basically you have two different kinds of special right triangle. Honestly, it doesn't matter to me which one we look at first, but we do have to look at one or the other. Anybody have a preference? The 45, 45, 90 is probably the easier one to look at, so maybe we'll start with that. We'll get our sea legs about us. Sound like a plan? Good. So you'll notice that all of a sudden it went from just memorizing things on this circle to now we're starting to get right triangles into the mix, aren't we? Uh-oh. You know what that sets up? The T word. 5 syllables. A study of mathematics related to trigonometry. Yeah, that's what the unit circle really is founded in. It's trigonometry. Okay? And the basis of trigonometry is geometry. So I'm going to go ahead and use, I think I have a special one of these right here. Yep. I want to flip this, though, from left to right. I want to flip this from left to right. Okay. And I also want to try to superimpose this onto the unit circle if I can. So I'll send my unit circle to the back, and maybe I'll even make it a little bit translucent like that. There we go. So can you still see the unit circle there? Okay. So here's this right triangle kind of superimposed. Let me make the unit circle a little bit bigger. And I'll go ahead and lock it down. There we go. Okay, so we got this special right triangle. It's pretty close. That's probably good. Okay. So if we think about this right triangle has a right angle. That's why it's a right triangle. We know that this is a 45, 45, 90 right triangle. So we know that this angle and this angle are congruent, and both their measures are 45 degrees. Does anybody remember how this side here relates to this side here? How those sides relate? Yeah, they're the same. Nice. So this is congruent to this, right? Okay. Yesterday we said something over and over and over. And when I do that, sometimes it gets under people's skin. I get that, yeah. A radius is a radius is a radius, right? So our radius, we know, for the unit circle is 1. So if we went, from here to here, that's going to be 1 unit long. Well, a radius is a radius is a radius. Notice that if we go from here to here, that radius equaling 1, that is part of our right triangle, isn't it? What part of our right triangle is that? See if you remember the names of right triangles. Nice, good. The hypotenuse, the hypotenuse, the hypotenuse. That's the longest side. That's the longest side. It's the side opposite or across the right angle, right? So our hypotenuse has a side length equal to 1. So what our task is, what our challenge is, what we want to find is a side length. Not the hypotenuse length, we already know that. We want to find a side length. So we want to find that length, which also happens to equal that length. You with me so far? All right. In algebra, when you're not sure how big something is, what's a nice variable to let represent that? X. So we'll go ahead and say that this is X, and we'll go ahead and say that this is X. And actually, this X could equal Y also, because our end goal, we also want the coordinates. We also want the coordinates of this point up yonder. So we'd like to be able to say that that point up yonder has coordinates something, something. So if we could find the X coordinate, that's the distance from here over to here. That's that distance from there to there. It's the same distance across here. That's going to be our X coordinate. And if we could find the distance from the vertex where the right angle is, if we could find that distance, that's also the same, and that's also going to be our Y. So our X and our Y coordinate are going to be the same. If only we had a way to set up an equation with right triangles. If only the Phoenicians and the Babylonians had sailed the seas and realized that if you go east 3 miles and north 4 miles, that you've gone a total distance of 5 miles. If only there were some kind of relationship that would put all that together. If you go west 5 miles and north 12 miles, is it 512? Yeah, then you will have traveled 13 miles from your beginning point to your ending point. Everybody picking up what I'm putting down, know what I'm going for? What mathematical fact we need to apply here? Some Greek dude proved it. He gets credit. Starts with P. Ends with an S. Right? What's his theorem say? The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the hypotenuse. You but know it better this way. A squared plus B squared equals C squared, right? So I guess we better be able to identify or label A, B, and C. What some people forget is that A and B are the lengths of legs. So this is kind of like our A, this is kind of like our B, and our C is our hypotenuse. So we know that we're going to have x squared plus x squared equals our hypotenuse. What's our hypotenuse's length? 1. So x squared plus x squared equals 1 squared. So let's see if we can't solve that equation. So 2x squared equals 1. So then we divide by 2. So we get x squared is equal to 1/2. And then we would take a square root and take a square root. So x is equal to the square root of 1/2, which is the square root of 1 over the square root of 2, which is 1 over the square root of 2. And this is not cool. I don't know if you remember this, but it's not cool to leave a radical in the denominator. So there's this idea of rationalizing the denominator. So if I multiply this by radical 2 over radical 2, that leaves me with radical 2 over radical 2 times 2, which is radical 2 over radical 4, which is radical 2 over 2. That's what we're after. That's going to be our x coordinate and our y coordinate. So our x coordinate is the square root of 2 over 2, and so is our y coordinate. Dude, this is pretty cool. Now, earlier on, we talked about the bow tie angles, right? So we should be able to find the coordinates of 3 more of those angle measures around the unit circle, just using the idea of quadrants and SIGNS signs. So let's go back to our bow tie angle here for a minute, to this one, and let's see if we can't figure out the coordinates. We already said that the coordinates here are radical 2 over 2 and radical 2 over 2. What's nice, what's oh so nice, move that up out the way for a second. Maybe I'll see if I can trace that. What's oh so nice is I can copy this, and I could just bring this on over here, because it's going to be the same thing over here, and I could go ahead and bring that down here too, and I could go ahead and bring that over here as well, but I got to fill in my SIGNS, my signs. My SIGNS, my signs. What happens over here to my signs? Which one gets the negative? The first one, the x, right? Let's go down to quadrant 3. Which one gets the negative? Both of them, good. And then over here in quadrant 4, which one gets the negative? The second one, the y. Okay. Are there any questions so far? Or comments? Or concerns? Or debates? There's a lot of things in the news you could debate today. I don't know that I'd go there, but there's a lot of things that are up for debate. So anytime you have a 45-degree angle, the x and the y coordinate have the same number. The signs might be different, though. The SIGNS, the signs might be different. One sidebar of information that's worth knowing, and I'm going to feed you little pockets of these trivial pieces of information, but the square root of 2 divided by 2, if you had to punch that into a calculator, it's approximately equal to 0.707. At some point in the near future, you're going to need to know that. Sometime next week, you're going to need to be aware of that fact. So if you punch in the square root of 2 divided by 2 on a calculator, that's going to be approximated by the decimal 0.707. Okay. All right, so we're at the midway point, really. Kind of. Because there's only other one kind of right triangle left, right? The 30-60-90 is the same as the 60-30-90. So I guess that's the one we'll look at next. 30-60-90, which is really a 60-30-90. The only difference is they kind of get turned. Got to be careful when I say that, but one of them is like, I don't know. There we go. And there we go, right? Basically same thing. So I'm going to go with it this orientation. I'm going to go ahead and flip that from left to right. And again, like I did before, I'm going to superimpose this on a unit circle. I'll send that to the back. I'll go ahead and make it kind of translucent so you can still see it a little bit. And we'll lock that down. And meow, we're going to look at this special right triangle, maybe. There it is. There it is. There it is. 30 degrees. So that's 30 degrees. So when I go ahead and label that, see if I can copy that, trace it. I'm going to bring this out here and make it a little bit bigger. Maybe I'll just put it on the next page over. Yeah, I'll just do that. It'll be easier because I'm going to need that room. I'll just bring that over here. Okay. Wow, that's big. So this little angle over here then, this angle here, what's the measure of that one? 30. That one's 30. Of course, this is my right angle. So the angle up yonder is how big? 60. So our 30, 60, 90 right triangle. Looking back at the unit circle, we know that one statement that I said over and over and over. Was it a radius is a radius is a radius? And the radius of a unit circle, the radius of a unit circle is 1. So guess what that tells us about this triangle? That our hypotenuse is 1. Good. So our hypotenuse is equal to 1 on this right triangle. Everybody doing okay so far? Awesome. When I taught geometry, I love having the smartboard. I really do, because having the smartboard gives you the opportunity to look at things and use some measuring tools like this and to be able to do this kind of thing. So if I look at this vertical height right here, I better change colors. That's not going to show up so well. I'm trying to go with something that's going to stand out. I guess this light brown. Okay, so I want to compare that to, I'll go with pineapple here. I want to compare that to that and see how they compare. See how those two compare. See if I can turn that without lengthening it at all. Maybe I should bring in the hypotenuse as well. So I got this one here. I got the weird brown one here. I'll go ahead and compare that to the hypotenuse. Go ahead and compare that to the hypotenuse. We'll see if we can figure out how these compare. I'll turn that without lengthening it. Does anybody at all see a relationship between those? There should be a pretty clear one. Should be a pretty clear one. Maybe I'll get another one of these brown ones. Anybody see a relationship there? What's the relationship? What's the relationship between this shortest side and this hypotenuse? The shortest side is half the hypotenuse. Awesome. Awesome. Good. So remember what we're trying to find, what we want to know. We want to know the coordinates up here. We want to be able to find the coordinates at this point right here. And if we go this distance from here to here, that distance is going to be our x-coordinate. And if we go from here to here, that distance is going to be our y-coordinate. And wait a minute, we said the hypotenuse is 1, and the shortest side, which is this side over here, that's half as high as the hypotenuse. If the hypotenuse is 1, then this is going to be 1/2, right? So that means then that our y-coordinate is going to be 1/2. And all we got to do now is just find our x-coordinate. Wouldn't it be nice if there was some Greek guy that had a theorem that would help us find this? Oh yeah, Pythagorean theorem again. A squared plus b squared equals c squared. Hmm. So we don't know what our x is yet, but we know our y is 1/2, and we know our hypotenuse is 1. So let's see if we can solve that. See if we can solve that. So that's going to be x squared plus, what's 1/2 squared? 1/2 times 1/2. 1 over 1 times, well, 1 times 1 over 2 times 2. That's going to be a fourth, right? And that's equal to 1. I want to combine this term with this term, so I better go ahead and multiply this 1 by 4/4 to make a fraction with common denominators. So I've got x squared plus 1/4 equals 4/4 now. So I'll go ahead and subtract a fourth and subtract a fourth. So I get x squared is equal to 3/4. And I square root this and I square root this. So I get x equals the square root of 3/4, which is the square root of 3 over the square root of 4, which is the square root of 3 over 2. And that's the last piece of the puzzle for all the coordinates all the way around the entire unit circle. And you're thinking, but wait a minute, we got the North Pole, the South Pole, the East Pole, and the West Pole. Those are 0, 1, and 1, 0, and all that. And the 45s have a rad 2 and a rad 2. So how's this the rest of them? You'll see. We'll put it all together. We'll put it all together. So this coordinate then, this x coordinate, is the square root of 3 over 2. So I don't know if you have ever heard of couples or mates or partners. But in life, there are some things that just always pair well together, like peanut butter and jelly, like chocolate and caramel. I like caramel, but not by itself. It's got to be contained in a nice pocket of chocolate. Or maybe there's a pocket of caramel in the chocolate, but I think you know what I meant. Sometimes there's identical twins. What I'm getting at is 1/2 and 1/2 are always teamed up. You'll always see those adjacent to one another, next to one another, when you're looking at unit circle coordinates. Oh, dang it. I screwed that up. I should thank myself so bad. I misspoke. Had the right idea. Identical twins. Identical twins are rad 2 over 2 and rad 2 over 2. Those always go together. I'm sorry. Those always go together. 1/2 does have a partner, and 1/2's partner is radical 3 over 2. And similarly, radical 3 over 2 has a partner, and radical 3 over 2's partner is 1/2. You're always going to see those things paired up. 1/2 is going to go with rad 3 over 2. Rad 3 over 2 goes with 1/2. Rad 2 over 2 goes with itself. So they're couples, they're mates, they're partners, they're twins. You're going to see these in ordered pairs all around the unit circle. And it's a lot easier than you might think. It really, truly is. Notice what the denominator is all the time on these. What's the denominator? It's always 2, right? That makes this pretty nice and uniform, doesn't it? Earlier I said there's this nook and cranny of information you'll want to know. I don't want to insult your intelligence, but of course most people know that 1/2 is 0.5. That's good to know. Radical 3 over 2 is approximated by 0.866. Sometime in the future, next week maybe, you'll need to be aware of that fact also. All right. So radical 2 over 2 is approximated by 0.707. 1/2 is approximated, well, 1/2 is exactly 0.5, and radical 3 over 2 is approximately 0.866. Okay. So let's see if we can't put this all together on another bow tie angle like this one. So we just went ahead and found this. We said that this y coordinate here, we said that this y coordinate here is 1/2, and the x coordinate is radical 3 over 2. So the awesome thing is, everything else that's a bow tie angle to that is going to have the same coordinates. Everything else here is going to have the same coordinates. So I can clone that, and I can slide that right over into here, and I can clone that again, and I can slide it right on down into here, and I can clone it again, and it's going to show up over here too the exact same way. But the SIGNS, we got to watch the SIGNS. We got to watch the signs. What happens over here in quadrant 2? Negative on the X. Quadrant 3, negative on both. Quadrant 3, we have negative on both. Quadrant 4, negative on the Y. Good. Okay. How are we doing so far? Good. On the other bow tie angle then, it's kind of like that last one, but we got to watch. We got to be real careful here. We know they're going to be fractions over 2. And I'll go ahead and clone that, put that down here. And I'll clone that, bring that one over here. And I'll clone that, bring that one up here. Okay, so there, and there, and there. So we know that this is going to be negative and negative, and negative here, and negative here. But now we got to figure out that relationship. So we're comparing that x to that y. It looks like the x is smaller than the y, right? The x is smaller than the y. Now this 1/2 and rad 3 over 2, or rad 3 over 2 and 1/2, regardless, those always go with 30, 60, 90s. And then the rad 2 over 2 and rad 2 over 2, those always get teamed up with 45s. 45, 45, 90s. So let's see if we can't get our order pairs right here. The x coordinate here, is it going to be 1/2 or radical 3 over 2? Good, it's going to be 1/2. So remember a minute ago I said that there's mates, there's couples, there's pairs, there's teams. And anytime you have a 1/2, it's paired up with a radical 3 over 2. So anytime you have a 1/2, it's going to be paired up with a radical 3 over 2. Anytime you have a 1/2, it's paired up with a radical 3 over 2. You have a 1/2, it's paired up with a radical 3 over 2. You have a 1/2, it's paired up with a radical 3 over 2. Okay. So at this point in time, you're probably thinking, oh my gosh, Mr. Minnick is nuts. He's expecting me to memorize all this stuff. There's no way I could do it. It's way too hard. It's really not that bad. It's really not that bad. If they're talking about the alphabet, you know how easy they say something is? It's easy as ABC. If they're talking about numbers, you're going to love this. You're going to love this. You're going to love this. How easy is it to memorize the coordinates of the bow tie angles of the bow tie angles. It's really easy. It's really easy. Super easy. Where do we live, by the way? Let's think about it. I know they don't teach geography anymore, but where do we live? Think about the globe, the world. The world. Here's the United States. There we are. Here's Ohio. There we are. Right? So where do we live? We live in the North America. We live in the United States, the greatest country in the world, some would argue. But we live in the northern hemisphere. Has anybody ever seen what happens when you flush the water in the northern hemisphere, how it goes down the toilet bowl the one way? Have you ever flushed the toilet in Australia? The water goes down the toilet the other way. If there's time, I'll show you the video. It's pretty fascinating. Just remember the things get flipped. Things get flipped down there in the southern hemisphere. Things get flipped. But other than that, how easy is it to remember the bow tie angles? It's as easy as 1, 2, 3. It's really that easy. If you don't believe me, I'll show you. Actually, it's 1, rad 2, rad 3. It's that easy, but you'll see. It's really easy. Okay. So, unit circle. Sometime next week, in about a minute and a half, maybe 2 minutes, you're going to have to fill in all the coordinates on all these bow tie angles. And I'm telling you that it couldn't be any easier. It's very fácil. Es muy fácil. Because you're always going to have a fraction and it's going to be over 2. Let me try that again. You're always going to have a fraction and it's going to be over 2. So every single time you do these, you're going to have a fraction over 2. Every single time you fill in these bow tie angles, they're fractions over 2. Every single time you fill in the bow tie angles, they're fractions over 2. They're real easy. How easy did I say they were? Easy as what? 1, 2, 3. Okay. Easy as 1, 2, 3. Oh, yeah? Yeah, check this out. Starting in quadrant 1. The unit circle is as easy as 1, 2, 3. If you don't believe me, watch. 1, rad 2, rad 3 down. Oh, that's how easy it is. Now keep in mind, rad 3 is paired up with 1/2, right? So it's 1, 2, 3 down, and then it's going to be 1, rad 2, rad 3 back up. You pick it up what I'm putting down here. Let's go over to quadrant 2. Quadrant 2, we know that all the x's get negatives. Don't forget about those signs. Let's fill in the rest of the signs. Quadrant 3, everything's negative. Quadrant 4, the y's are negative. So when we're in the northern hemisphere, when we're in our home area, the unit circle, filling in the bow tie angles of the unit circle is real easy. How easy is it? It's as easy as 1, rad 2, rad 3 down. 1, 2, 3 down, 1, 2, 3 up. 1, rad 2, rad 3 up. Wow. Dude, that's cool. That's too cool for school. Now, you don't want to get too overzealous here. There is a caveat to watch out for, and the caveat to watch out for is what happens in the southern hemisphere. In the southern hemisphere, things get flipped, don't they? You got to remember about your bow tie angles. So what I'm getting at is from here to here and here to here, we're going to be wearing that nice, shiny bow tie. So when you get to the southern hemisphere, it's not going to be 1, 2, 3 down. It's going to be 3, 2, 1 down. And 3, 2, 1 up. Okay? That's where a lot of people get this twisted. They kind of screw it up. But think northern hemisphere, southern hemisphere. Northern hemisphere, 1, 2, 3 down. Southern hemisphere, it goes the other way. 3, 2, 1 down, and 3, 2, 1 up. So you could probably think of it in the north. In the north, it's as easy as 1, rad 2, rad 3. Down under, down under, down under, it's a countdown. It's a countdown. How do you count down? 3, 2, 1. Rad 3, rad 2, 1. It's a countdown. Down under. Okay. These are little things that I use to help me memorize this stuff. Of course, in the context of everything, don't forget about these other coordinates. You know, you are still going to have to retain that information. And those are easy ones to screw up. Over at the East Pole, what's the coordinates? Is it 1, 0 or 0, 1? 1, 0. West Pole is going to be negative 1, 0. Up north is 0, 1. Down south is 0, negative 1. Okay. So that's it for part 2. That's all the coordinates of the unit circle. On Wednesday of next week, I'm going to expect you to be able to fill in not only all the angle measures in degrees, but all the coordinates all the way around too. That'll be a 32-point test/quiz. Don't write the answers on your hands. That'll be on Wednesday next week. Tuesday is just going to be the angle measures and the coordinates at the poles. Okay. So it's been real. It's been fun. I'd like to give a shout out to the future Mr. Minnick. I'd like to give a shout out to everybody who's been working hard. And I'd like to give a word of encouragement to those who feel lost. This unit circle stuff, this is your chance to get with the program and get up to speed and get caught up. So have a great day. Have a great weekend. See you. Good.